Hello, everyone. My name is Max Herzog. I'm a program manager with Cleveland Water Alliance, and it's my great pleasure to welcome you to this month's edition of Water Data Forum, Innovations in Remote Sensing for Water Quality. Water Data Forum is a monthly web series that's being presented throughout 2021 by Cleveland Water Alliance, the Midwest Big Data Innovation Hub, and the Water Environment Federation. This has been a great partnership, and really excited to hear from another excellent panel of speakers today. Just a couple of housekeeping notes before we kick things off. I'd like to ask you to please submit your questions throughout the presentations using the Q&A box. You can find that in the little toolbar at the bottom of your screen. It's important to point out that it's distinct from the chat, and we tend to look at Q&A for those questions. We don't have to weed it out from other things. So please submit those questions in the Q&A box, and we'll be serving those up to the panelists at the end of the session. With that, it's my great pleasure to introduce our guest facilitator for today, Dr. Frank Mueller-Karger. Dr. Mueller-Karger is a biological oceanographer who conducts research on marine primary production and biodiversity by combining traditional oceanographic methods, satellite remote sensing, and large data sets. He has fostered significant international collaborations to better understand life in the sea and co-chairs the Marine Biodiversity Ocean Observation Network, or MBON. Frank was a member of the U.S. Commission on Ocean Policy appointed by President George W. Bush, and has served as a member of the National Research Council's Ocean Studies Board and on several NASA science teams and planning committees. He's received awards from the U.S. Environmental Protection Agency, NASA, the U.S. National Ocean Partnership Program, and the U.S. Congress. Frank has authored or co-authored over 200 scientific publications. He is of Hispanic descent and speaks fluent Spanish and German. So with that, it's my great pleasure to hand things over to Dr. Frank Mueller-Karger to introduce the rest of our panelists.
Thank you, Max. It really is my pleasure to serve as moderator for this panel. Today we have Dr. Kate Fickas from Utah State, Steve Grubb from GeoAquaWatch at the University of Wisconsin-Madison, Lee Pullmanson, the University of Minnesota, and Christine Lee, who is at NASA headquarters and also the Jet Propulsion Lab. So I think that we can go ahead and start with, in that order, pretty much. And each one of the panelists will have a few minutes of a presentation, and we can get into the questions.
Great. Thanks, Frank, and thank you so much to the organizers for inviting me in this panel. I'm humbled to be up here with several folks on this panel discussing innovations in water quality in remote sensing. So I'm a harmful algal bloom program coordinator for the Department of Environmental Quality. Previously, I got my doctorate at Oregon State University in remote sensing, and then spent some time on the East Coast of the United States using UAS and Landsat mostly to monitor wetland and aquatic ecosystems on the coast to look at how they were changing under sea level rise. The position I took at Utah was a significant departure from my academic career. They invited me in mostly to be in charge of the harmful algal bloom program, but I weaseled my way in to make sure that I was also in charge of remote sensing as well, and incorporating remote sensing into their water quality scheme. So this slide, a lot going on, but I just wanted to present a smattering of the ways that I make sure that we're incorporating remote sensing into public health decision-making at Utah DEQ. So we have a really robust harmful algal bloom monitoring program. We monitor about 70 lakes consistently, either weekly or monthly during the recreation season. We collect about 2,000 lab samples. I'm involved at NASA Goddard looking at new algorithmic development for Landsat and Sentinel-2 and Sentinel-3 for lakes over the state of Utah. But really, that's all very tech-based remote sensing. And I came in and I learned at Utah, we have a system where it's our local health departments that are making advisory decisions. So In my department, we analyze the lab data and the science, present best available data, and then make advisory recommendations whether or not to put a lake or reservoir or river on an advisory to protect folks who might want to recreate there. So the partners I work with are really smart. They're environmental epidemiologists, but they're rarely educated in remote sensing, or they just have so much on their plate, they're not necessarily interested in learning more about remote sensing. So I've slowly weaseled my way into their hearts by using remote sensing and specifically Sentinel-3 at this point, data to inform advisory decisions when it comes to harmful algal blooms. So we're able to use remote sensing to first prioritize where we're monitoring. We can look at hotspots over the years, either through Landsat, the deep temporal, the time series going back to the 1970s with Landsat, and then on a daily basis over the recreation seasons in the past several years with Sentinel data. So we not only prioritize where we're monitoring, where to protect public health with remote sensing data, we can target very specific beaches and sites within a water body. Then once we detect a harmful algal bloom with in situ data, we're actually able to make very targeted advisory decisions based on remote sensing data. So we can tell local health departments and explain to them exactly where the HAB has occurred and where would be most protective in placing an advisory. We have to strike a balance here in Utah with most of our big water bodies also being state parks, and the only way that state parks make their money are through recreation tickets. So when we close down a water body, it's a big deal for the state. So we have to be really balanced. So not only do we have satellite data, one of my graduate students, 50% of my time is spent in research. One of my graduate students has been working on UAS data to incorporate that. So once we detect something with either with in situ data or with satellite remote sensing data, we're able to go fly a drone and get a much clearer, finer spatial extent of or spatial resolution of where the HAB is occurring. So in this picture, we can take a look and see that it's a lake-wide harmful algal bloom, the picture right above the drone. And in that case, we make an advisory recommendation to protect public health by closing the entire water body, not just a beach. We're also able to link this data to telemetered buoys that measure phycocyanin, chlorophyll, and other water quality measures so that we're able to link remote sensing data directly to our in situ lab data. So we have 3 tiers there. We have lab data that we send to environmental chemistry. We have our buoy data with fluorometry, and then we have our remote sensing satellite data from several different sensors. I also want to mention a cool project we're working on in Zion National Park, which had a really severe benthic cyanobacteria bloom, so bloom that occurred on the riverbed as opposed to being a scummy film or water column bloom that you might see normally in a lake or reservoir. And there's quite a gap between being able to monitor planktonic or lake-wide harmful algal blooms from benthic harmful algal blooms. So we're incorporating UAS data. That's my grad student Nathan there in that picture. We're not allowed to fly drones in national parks, so he had to set up a painter's pole. We're incorporating spectral data there to try to get a tool going for the National Park Service to be able to do rapid monitoring of benthic spatial extent, benthic cyanobacteria spatial extent going forward. So again, that's just a quick and dirty of what we're doing in Utah, making sure that I'm able to incorporate remote sensing data to inform public health decisions every recreation season.
Okay, and we will next go with Steve Grubb. I would like to remind the participants, anybody on the call, to send questions to the Q&A button, please.
Thank you, Frank. And as Kate said, it's a pleasure to be here this afternoon and tell you a little bit about my work or the work of my organization. So good afternoon. My name is Steve Grubb. I am the director of GEO AquaWatch, GEO meaning Group on Earth Observation. I'm also a research scientist here at the University of Wisconsin in Madison. In my previous life, I worked for the Wisconsin Department of Natural Resources in their research branch, where I had 1 foot in the research world and 1 foot in the management world, and we're working on applied science related issues. For those of you who are unfamiliar with AquaWatch, we're the water quality initiative within GEO, with the goal of building the global capacity and the use of Earth observation derived water quality information to support water resources management and decision makers. This work is mainly volunteer effort, and we're supported by many dedicated water quality professionals around the globe. Right now, I think we have about 350 individuals are part of our group. If you're interested in participating in one of our activities, which is one of my objectives today, again, to make you aware of GEO AquaWatch, or want to participate in one of our working groups, we would welcome your talents. In particular, we're really interested in hearing from the end user community. So if you look at the slide that's on the screen here now, we have 5 objectives that are backed up by five working groups. And they're in the dark, the maroon colored circles. Starting on the top with the outreach and end user engagement, which again is one of our objectives here today. But we're interested in facilitating kind of effective partnerships between the end user community, the producers and providers of this Earth observation derived water quality data, and really understanding the issues that are out there and what products are needed from the end user community. Going down on the right-hand side here, observation and data. That working group is mainly focused on things like improving the analysis and integration of the in situ with the remote sensing world, things like sensor technology, algorithm development, issues such as that. Thirdly is products and information. Again, we're interested in what are the products that are needed out there in making fit for purpose products. Fourthly is the distribution, access, and visualization. As it says, this is an effort to support tech transfer to make this data more available to the end users and to create visualization tools to make this easily accessible. And finally, education and capacity building. We're an advocate for increased education and capacity to use this water quality information for decision makers. So I think I'll quit there, and maybe we'll have a chance to dive into this a little more as we enter into our discussion. But the focus of all this is to develop this water quality information service. Thank you.
Thank you, Steve. Next, we have Lee Pullmanson.
Okay. Yeah. My name is Lee Pullmanson. I'm a research scientist from the University of Minnesota. Let's see, and I'm going to be talking about some of the work I've been doing in Minnesota. So I have over 20 years experience using satellite remote sensing for Minnesota's 10,000 lakes. And the recent satellite imagery, we have Landsat 8, Sentinel-2, and Sentinel-3. There's been some big improvements with higher spatial, spectral, radiometric, and temporal resolution. So really for the first time during my career, we have an opportunity to build a near real-time water quality monitoring system. So that's what we've done in Minnesota. So we have all this great new data. It's downloaded to the ground stations. And then from there, we can get machine-to-machine access into the Minnesota Supercomputing Institute. And with the help of my colleague, David Porter, we can start processing the imagery. First thing we're going to do is normalize the imagery with atmospheric correction. And then from that, we're going to mask off any anomalies, pixels, things like clouds, cloud shadows, wildfire smokes become a big deal. And then aquatic vegetation that's in the water. So we mask off all those. We have just clear water pixels. That we can link all of the field measurements to the satellite imagery, the clear satellite images available, and then develop water quality models, apply those models back to all the lakes on different images, and come up with maps, data statistic summaries. So here's an example of our data. We just released this about a month ago. This is chlorophyll level data. Also have clarity and CDOM. Oops, gotta go back. Let's see. Let's try that again. Okay, here we go. So this is 2017 through 2020 monthly chlorophyll levels. As you can see, this is the meteorite problem area. You see in this late summer, you have a lot of blooms in the agricultural areas, just to the west and the south of the metro, plus a few of the lakes in the metro area. So that data has all been added to our lake browser. And the lake browser is an online resource where we have many thousands of unique visitors come monthly to get information about their lakes. It was originally established in 2002. Includes all of our previous assessments using manual methods from 1975 to 2015. It includes over 10,000 lakes, and those assessments have been at around 5-year intervals. So it's been a bigger advancement with this automated system, because now we have monthly CDOM, chlorophyll, and clarity data from 2017 to 2020 currently. And I'm just going to go to our website here. So you can go to pixel level or lake level data. You can zoom into a lake. You can pick a lake. From that, you can get a full report. You can see the temporal trends over that time period. We have tabular data. And then when we get to the seasonal mean, and then when we get down to the automated system, we have now monthly measurements for those. We've ranked the lakes for seasonal averages, so you can see how your lake ranks from other lakes for different for water clarity. We also have CDOM in there, chlorophyll, and then some land use stuff. And with that, I will look forward to more discussion.
Thank you, Leif. And now we have Christine Lee.
Thank you. So as I'm also really happy to be here. Thank you for the invitation and the opportunity to share some of the work that we've been doing. So I'll offer 2 perspectives today. One from the kind of hat that I wear, representing the the NASA Water Resources Program that's based at headquarters, and one that's more from the NASA satellite mission perspective. And so I'm also, in addition to being an applied scientist and a researcher, I also am an associate program manager for the NASA Water Resources Program. And the main focus of the NASA Water Resources Program is to support the water resources management community by funding and cultivating projects to more effectively utilize NASA and other remote sensing assets. These different satellite assets can be used to derive water-related information, including water quality, but we also support a wide variety of projects that also span things like water use in agricultural contexts, improved monitoring of drought onset, soil moisture, stream flow forecasts, as well as impacts of climate change on water resources, and effects of, for example, groundwater pumping on our landscape. So being able to look at the landscape response in terms of subsidence. So there's a wide variety of assets. And I just wanted to mention that as the broader landscape of our discussion today, that's more focused on aquatic and water quality applications. And so the next kind of perspective that I wanted to offer was along the lines of NASA work related to satellite planning, development, implementation, and operations. And so in May, NASA released their announcement that they were committing to the design and development of an Earth System Observatory Core that includes these different satellite missions. And that part of this commitment was to help mitigate the effects of climate change. So you can see across the bottom panel here that each of these missions has a different kind of science and applications focus. But that the one in the middle, noted as SBG, which is the one I'll talk about in a little bit more detail, actually spans a very diverse set of science and application priorities, from terrestrial to aquatic. And the three that are on the right, so SBG, Glimmer, which looks like some of the text is cut off, and PACE, have a very strong focus on improving our understanding of aquatic systems, from both inland to coastal to ocean systems. And they are all going to be at least partially reliant on measuring, utilizing imaging spectroscopy as part of the core data sets. And so if you go to the next slide, I'll just briefly mention kind of where we currently stand with respect to the surface biology and geology, or SBG, mission. We just completed a several year kind of architecture study where we considered a wide variety of different hardware and platform considerations. And it was essentially a feasibility assessment to try and match the optimal hardware with what we can get on the science and applications output. So can our measurements from a particular set of platforms actually be used to address our kind of key science and applications priorities? And can we do it within cost? So we're considering science and applications value, hardware capability, and engineering and cost. So hardware, engineering, and cost. And the outcome of that architecture study was that we are proceeding with a 2-platform system. One that will measure, we're calling SBG Light. So this would be a wide swath visible to shortwave infrared imaging spectrometer with a 16-day revisit, 30-meter spatial resolution. And our second platform would be measuring in the mid to long wave thermal, along with having a V-near camera attached to it. And that would have approximately a 3-day revisit and a 60-meter spatial resolution. We are also leaning into international partnerships to increase the temporal revisit of these platforms. And so by partnering with our European colleagues, we expect to be able to get a thermal revisit of 1 day. And on the visible to shortwave, we expect to get approximately a weekly revisit. And the aquatic community has been extremely involved in providing feedback into this process. And so this has been incorporated in a number of ways, which I will talk about in the next slide. And so we've primarily been, okay, so the yellow box should actually be highlighted over the aquatic algorithms part of the table. But so the aquatic community, including those who understand and work in the water quality and coastal applications area, have been meeting through the aquatic studies group that are co-chaired by colleagues at NASA Goddard and NASA Ames, Kevin Turpey and Leanne Guild. And some of the key outcomes of this aquatic studies group is feedback to the SBG mission, which if you click on the next slide, a block should put, okay, great, which includes the consideration of aquatic products. And here's a candidate list of products that SBG is currently considering that are very strong candidates for what SBG might produce as standard products in the future. ASG has also provided input on calibration and signal to noise needs that SBG has also taken into consideration. And so for this community that's joined us today, if you're interested in providing input into how SBG is proceeding, we're not launching for another 6 to 7 years. Now is actually a great time to get involved. If you're interested in the data sets, it's also a really great time to get involved as we start building out our library of prototype data products that can be used for training and testing. But I would emphasize that if you provide feedback at this stage, that could have really vast implications for how the SBG operates and thus translated value to the water quality community. So if you're interested, I would encourage you to reach out to either Kevin, Leanne, or myself, and we would be happy to talk with you further on that. I think that's my last slide. So thanks for listening and happy to discuss further.
Thank you, Christine. So I think that we'll spend, now we have about half an hour where we can ask questions or have a conversation on these various topics. I have several questions. I see some are coming up. For example, maybe Leif or Kate can talk about whether some of these satellite observations are paired up with in situ observations.
Yeah, so in Utah, we use this approach. We have about 6 water quality buoys, multi-parameter sondes that sit out in the lake, trying to get an image spectrometer, which it sounds like maybe that question is also asking about with upward and downward light sensors. But we, both for our own edification as to how our buoys are doing in terms of being able to link up to remotely sensed data, we do that, and then we also provide folks from NOAA, NASA, EPA, and USGS our data to act as validation. And it's in a particularly selfish way for us because we want those algorithms that everybody's talking about here on this forum to work really well in Utah. So the more data that we can provide with in situ data, the better it works in our neck of the woods.
Yeah, in Minnesota, we use a lot of in situ data. We have a lot of in situ data. Have good water quality monitoring programs. So we have lots of data, and so I think for matchups with satellite from 2019, it was over 6,000 measurements within one day. So we have plenty of data for that.
That's impressive. So I'm going to ask questions on really generally 3 lines of thinking. One is if you can give more success stories or examples of how you apply these data. Then also some of the challenges and gaps that you have, and then some more visioning. I had a question, for example, most of you talked about freshwater inland applications. And so I have a question. What are the differences, or how do you use this if you're interested in coastal zones, or you know, is there such an issue as water quality concerns in the middle of the ocean?
I'm a water scientist, so I don't have any information on ocean stuff. So that would be you, Frank.
No, so this is interesting. I'm always wondering. In the past, many years ago, limnologists and oceanographers were pretty much one community, and there's been a little bit of a divergence. But we use the same satellites, the same cameras to look at the very same problems in coastal zones and in inland communities. So I wonder to what extent the water quality that I can measure on the coast is a water quality. Is it the same thing when I look at a lake?
I think not, because there's a lot more. There's a lot higher concentrations of things like the chlorophyll, and then also like color dissolved organic matter in our waters. Minnesota, we have lots of CDOM in our waters, and there's a distinct difference between our very algae-trophic lakes than there are from our other lakes, and most of our, our models work better with the ones with a little CDOM and a little bit of algae and stuff in them.
Yeah, Kate.
I also think you have an interesting dynamic on the coast. So like a lot of my work is operating under anomaly detection. And I know working in coastal wetlands with tidal cycles, storm surges, just the currents that dominate those processes offshore, you're dealing with a lot more interesting temporal dynamics going on. So from my perspective, potentially warning folks, I don't know, in the middle of the ocean, but right off the coast, potential recreational risks or fishing risks or die-offs from water quality issues. I could see there being a lot more a lot more to consider when trying to analyze and get your head around that type of problem.
Yeah, this is Steve. I would just add to that as to reiterate what they've just shared with you. I mean, as you go from open ocean, which is generally the signal is derived from chlorophyll. Chlorophyll is about the only optically active substance that's called contributing to it, and at much lower concentrations. And as you go through this transition coastal waters to inland waters, they get more complex and there's more stuff there. And so the algorithms and the approaches get more complicated. But again, our technology has been evolving quite rapidly here. And so AquaWatch is interested in both the coastal and inland waters. And I would just add that there's a European project which has just started this past year called CERTO, which is focused on these transition waters and coming up not just with one algorithm, but a suite of algorithms depending on where you are in these transition waters. So you classify the waters, then apply your algorithm. But it's a tough issue.
It's a tough issue, and I come from the perspective that the land and freshwater and the coastal ocean are connected. In many ways, when we look at the maps from satellites, we often see the ocean pictures with a land mask applied, so you see nothing on the land. And sometimes when you look at the ocean, the oceanographers put a mask on land, and you see nothing on land. And yet they're a continuum in an ecosystem where a lot what happens inland moves down the rivers or other types of water discharges and affects what's on the coast. So I hope that at some point the ocean and the land community and the freshwater community all come together and start looking at the planet as one planet and not as a masked planet where we block each other off just to focus on our process. So along those lines, we know that these products have some uncertainties, or not to call them errors, but they're true uncertainties, and the product that in the ocean, for example, we characterize when we talk about chlorophyll like a percentage of the number that we're looking at. So typically, we said if we see any value, then we can estimate or assume that the error or the estimate, the uncertainty in the estimate is about 30%. And so as Leif mentioned, the values in freshwater environments are often very, very high, compared to an oceanic value. And so I wonder how we handle uncertainty when we present this information to the public. And maybe I'll have start with Christine, because she's dealing with this from an applications point of view, but I'd like to hear from every one of you.
Yeah, well, so I will say relative to applied science projects, we definitely tie all of the satellite derived estimates to in situ measurements. And I know that there's a lot of instances where people might, if they're, for example, developing something that's a global model or what they consider a global algorithm, they might not always do that. But in an applications context, it's critical that we see satellite-derived products as an enhancement to an existing monitoring system, whether it's in situ sampling or buoys or so forth. And so I tie all of our variance by comparing our satellite-derived estimates to what we're seeing on the ground and put it in the context of what our partners are using.
Yeah, we see about 30% error as well in inland waters.
Yeah, that goes, I think Christine said it really nicely, is that it's an enhancement. That's how we use it. And at the state level, we also try to go by recommendations output by the EPA in terms of what thresholds we should be using and what parameters specifically we should be using for water quality monitoring, for health advisories. And right now the EPA has said there's too much uncertainty in satellite imagery to be able to have regulatory power when enforcing or calling, things related to public health. So I try to push that as far to the limit as possible. We're also in Utah, lucky and unlucky. We only have really one oligotrophic lake. The rest of them geared towards eutrophic, and most of that is actually cyanobacteria, as opposed to a mix of all phytoplankton. So when we have, so we're able to use chlorophyll a lot more reliably than having to make sure that we have a mix of both phycocyanin, which comes from cyanobacteria specifically, as opposed to all photosynthetic reflectants. So we're able to tie it really closely. And I think once you inch, like I was saying, I work with epidemiologists who would rather not have one more thing crammed into their brain about protecting public health. But once you inch them closer and closer to building capacity and trust, and understanding where the satellite imagery is coming from, there's a lot more ability to be able to use it in a really holistic way.
Yeah, I think it's a great question, Frank. And I think, you know, when the satellite community is generating these values, it's their responsibilities to put errors about those numbers. And just kind of fortuitous, I happened to print out something. I didn't know you were going to ask that question, but EPA did this survey, and in this paper by Schaefer et al. In 2013, it said almost unanimously, interviewees wanted assurance that the satellite product could be validated and include reported accuracy and error estimates for their particular water bodies. Interviewees agreed that if a product was proved to provide an accurate measure of their particular water body of interest, they would be open to using those products for their monitoring, research, and assessments. So, you know, it's somewhat of a, you know, success breeds success, and as we build confidence, I think we'll see more uptake of this information. And just one other plug for, we wrote a proposal to NASA, which is going to be funded here, to run a workshop. It's going to be next June now, strictly on validation of these products. It's going to be held here in Madison. But you know, when we've asked the remote sensing community, you know, what are some of the top issues, this whole concept of validation is really important. So you're spot on there, Frank.
Yeah, I think that one of the things that we often miss in the value of the data is one. Kate mentioned, what is the source? Is it a point source, or is it some other type of event? And so the satellite data allows you to look at spatial patterns over time, and sometimes you can identify where something is originating. So that's one application. The other thing that Kate mentioned that is very interesting is, in some cases, you may not care about the absolute value of what you're measuring that much, but about the change. If you're measuring things the same way over and over and over, and you see something change, then that's an alert or a flag of some sort. And so that's something that we should appreciate. So there's a question in the chat here, and the question and answer on this is a question I've heard asked for almost over 40 years, on how you use satellite data and whether you can measure nutrients, for example, phosphorus directly, or how do you extend a color measurement to something like a nutrient measurement?
With satellite remote sensing optical, we can measure optical active constituents, and we're not going to be measuring nutrients. Yeah, many lakes, there's a very strong correlation between phosphorus and chlorophyll. So if you want to infer what phosphorus might be, you could probably use enough measurements to infer something like that. But we really don't like to measure things that we can't see with the satellites.
So yeah, that's a function of an algorithm. So it's empirically based, and you can relate one property to another by proxy, no?
By proxy, yep.
Yeah. Anybody else want to answer that?
I think it depends on that application. Like we said, it's we would get a lot of blowback at DEQ if we tried to link, especially if we were interested in a point source pollution contaminant. Then again, going after something regulatory based on a largely algorithmic derivation of relating nutrients to satellite imagery, it'd be a tough sell. However, you can, we've looked at linking contamination events. So you can look at, you know, TSS going into a lake from a river or another overspill, and that can flag monitoring of excess nutrients after that.
Another question here is whether all these data are real time. Can people use the data if they're going to go to a lake with a family? Is there value in checking these data in real time, and how can you access it?
For us, I guess it's, I mean, that's our goal, is to make it real time, near real time. We can process it in near real time. Right now it's the roadblock is posting it. So we haven't set up our website to actually post it that way.
I'll just briefly comment on the latency question as well. From the perspective of SBG, we definitely took latency into consideration even at this early stage, because we have to consider downlink and onboard processing capabilities, so that, you know, if we wanted to accommodate that in the future, and it looks like the mission is planning to, you know, that we could get the data down within, you know, a couple of hours of acquisition. But even that said, there's other considerations there, which is going to be on the data quality side. Even if we could process the data very quickly to a near real-time product, well, going back to Frank's earlier question, we're going to have to communicate on what the data quality and uncertainty is of those near real-time products. Some of the other missions that I work on, you know, we consider good latencies to still be, you know, 24 hours or less, but that's not near real time in terms of when it was acquired to when it's being provided. So that's definitely another consideration. I also wanted to make sure we answered Ed's other question about depth from surface. So in general, I would say that that's probably a different set of measurements. So we can look at bathymetry using LiDAR, and we can look at lake height using altimetry. So that will likely be a different set of measurements, but it is possible through other assets.
Thank you, Christine. If the water is very clear and it's not very deep, then we can see the bottom. So that there's some applications there, typically in coastal zones. So one question comes here on whether Utah, but I'll ask anybody, and also Leaf, whether you basically cook your own algorithms, or do you use, like Christine said before, some universal type of algorithms?
I use them all. So one of the main sources of data, which I would, like Christine said, I think 24 hours is pretty fabulous in terms of turnaround time. So we have the national cyan product. Again, that's that collaboration between NASA, NOAA, USGS, and EPA, where they're putting out cyanobacteria index, CI, daily. So I'm able to download that data, process it, and spit out statistics for our local health departments and public health officials on a daily basis for all of our waters across the state. Otherwise, when I'm looking at different satellite missions like Landsat or Sentinel, I'll often see which ones work best at different reservoirs around the state, because we have differently optic lakes around the state, and they don't all work the same within each lake. And we actually have very specific Utah Lake, which is kind of our Sentinel Lake. It's only 9 feet deep at its deepest, but it's still 45 miles long, 20 miles wide. So it's one we monitor frequently. And 3.5 feet right now with the drought, not all the algorithms work correctly. So my answer is, sorry, I use a lot of them for monitoring using the finer spatial scale satellites, but that cyan chlorophyll index or cyanobacteria index is really useful.
Yeah.
And as far as,
go ahead, Steve.
As far as the near real time question, I mean, this is something which again is evolving over time, and we're getting there. You know, when I mentioned the water quality information service, I mean, that's one of our dreams or goals, is to kind of create this system similar to what the National Weather Service would be, but for water quality, where you could go in and click and see what your water quality conditions are that day. I think there's always going to be this latency due to, processing of imagery. And I mean, we're talking, terabytes of data, just, it's streaming every day. And so it's a lot of work, and we're not quite there yet, but there are some examples of, it was mentioned here and also in Europe with the Copernicus project and some of the land use or land products. There's a water quality component to that. The Coast Watch, has some really up-to-date data for coastal areas.
I think for Minnesota, yeah, we have, I mean, we used to do these every 5 years. The satellites were every 16 days, with Landsat being pretty much the only name and, the only satellite, which really hasn't been used in coastal areas very much. It's more for, I mean, there's lots of opportunities for daily coverage for the oceans, but for inland waters, we've been reliant on Landsat really for, over 90% of our lakes. So having with a Sentinel-2 and with the Landsat now, we got a lot more temporal coverage. So the near real time is, it's so much closer to it now, because we could actually start processing any clear imagery that becomes available, where before it might be a month or two before you'd actually get clear imagery. So if you're, especially in Minnesota, we have lots of cloud cover. So you're not going to have, every time the satellite comes over, you're not going to get some data, but if you have enough time steps in it, you're going to be able to get imagery. And that's kind of our approach. And once we're able to acquire the imagery, we can process actually pretty quickly. Our algorithms are all developed with field measurements, so they're field derived, but the models we develop from 1 year work just as well for the next year. So for the automated system, it's more just running the algorithms we've already developed and then just validating them as the field measurements. The field measurements we typically won't even get till the next season, when they're available to use. So.
Wow, so those are important challenges. So one other question here on challenges. We've talked about coastal zones or the ocean and lakes, but what about rivers? How are these technologies at the point where we can say something about the water quality in rivers?
A lot of the rivers is more of a spatial component, and a lot of the rivers are too narrow. If you have some wide spots in the rivers, you can collect it. It's really different constituents that are more important for the water quality, but some are the same. But if you look on our lake browser, we do have plenty of river stretches that are included in our lake browser at the pixel level.
Great.
We're in
So
Utah. Sorry, go ahead, Frank.
No, go ahead.
I was gonna say that's where drone data comes in handy, and that's where we'll deploy both multispectral and hyperspectral drone missions for targeting, especially right now in Utah, we have a huge benthic cyanobacteria problem. So it's really lovely to have a tiered approach. So you have satellite imagery, you have your drone imagery, and then you have your in situ data as well. So I encourage the use of UAS unoccupied aerial systems for anybody who's interested in monitoring rivers, even at a smaller spatial scale. We've had a lot of success.
Yeah, that's a great point, Kate, because this is where I was going to go. So we've talked a lot about the different, the balancing act between spatial resolution, temporal resolution, the spectral resolution, and the quality of the data. I mean, if you have high spectral resolution, you may have to sacrifice something else in the spatial resolution, or in temporal resolution is, we want to measure things all day long everywhere, and that's often not really possible. So and now we're really getting into the age where hyperspectral data is becoming public. It's NASA's planning mission. The Europeans have some prototype missions. So what's the advantage of hyperspectral data in this space, time, spectral, high data quality environment?
I wish I had a slide to help kind of visualize this, but most of the current assets that we have are what we consider multispectral, which means they measure in certain chunks of bands, and maybe on the order of 10 to 20 chunks of bands. And these are typically optimized for imaging as well. So like the Landsats and the Sentinel-2s. And so the platforms that I would say are most useful for inland water quality, especially things like smaller lakes and rivers, have the spatial resolution of the land imagers, but don't necessarily have the spectral qualities that we need on the aquatic side. But we're hoping that SBG and our European partners will help address that by having a really great signal to noise ratio. So you might imagine that we can estimate reflectance in these chunks of bands, but when you have hyperspectral, you now have more of a continuous spectral profile from which you can derive or extract information about optical properties within the water column and relate that back to these geophysical parameters or biological parameters that we're interested with. So it's this much just greater density of data that we can use to derive those properties. I don't know if others want to weigh in on that, but there are some really great visuals to help kind of communicate that point.
Yeah, with the hyperspectral, I mean, basically, it'd be great to have the size of the files get much larger, harder to process. You kind of, I mean, if you wait for 10 years for the next great thing to come out, you're never going to get anything done. So I guess that's why we've been using Landsat for over 20 years, where it just became popular the last few years, and the last 10 years probably, where for our first submittals of papers, it was like, Landsat can't do that, but it's become proven quite consistently around the world that it can. So I think you got to use what's available, the resources what you have available for the satellites, and hopefully have your input to the next satellites that are coming out in 8 to 10 years, and then look forward to those. But if you wait around, you're not going to get much done.
Leif brings up a good point. You mentioned a 20-year time series of Landsat. One of the limitations with Landsat before, Landsat is now close to 40 years. And for a while it was private. And so it was very hard to get data, very costly. And today we have a large number of private companies that have satellite data. And we've been talking about spatial resolution in the order of 10 meters, 20, 30 meters in this conversation, even 1 kilometer for many of the ocean looking satellites. And yet some of the commercial data are coming down to centimeter level pixels, and they give you data all day long. And some satellite companies have close to 150 satellites flying at the same time, and some give you multispectral video and so on. So how do we, in the science community, where we're looking for really high quality data, global coverage, how can we partner with the private companies that are providing these kinds of satellite data that are revolutionizing remote sensing in a public manner, but it's still costly?
And I can comment again from the NASA perspective, and Frank, and others on the panel are probably aware of this already, but there is a NASA partnership with commercial small sats now. We're trying to work out a longer term agreement as to whether NASA does a longer term data buy to make the commercial small sat data more accessible and available to the general community. But there have been a number of RFPs that have come out, seeing if the NASA and extended community can help kind of evaluate those commercial products to see kind of what are the trades between what NASA assets are providing versus the commercial small sats. And I definitely want to acknowledge the huge and tremendous value of Landsat and Sentinel-2. particularly for just this long-term record. And I mean, just the thermal record alone from Landsat, I mean, that is really helping us kind of understand, you know, the impacts of climate change, looking at global lake temperatures and so forth. And so absolutely, we need that data. We continue to need that data. And so I can't emphasize that enough.
Well, we're reaching the close of the hour. I wonder, Max or Adam, if you have anything that you want to close with, or if any of the panelists have any final words.
I'll just say, with following on Christine's and that last question, Frank, and that not every single remote sensing application has to be the end all be all. I think that the small private satellites can be tremendous for very specific applications, as long as we're making sure that we correctly communicate and identify accuracy or, you know, any issues like that. And I think that's the same for every single remote sensing application. We can do so much, but none of it can do it all. And we have to really make sure that we're communicating to partners who may not be as remote sensing tech savvy exactly what can do what, so that we're using it appropriately.
Yeah, we just had some communications or working on a development of a proposal to look at shrimp farming in Bangladesh, and you know, what are the most appropriate satellites, and we've talked about these small sats that you mentioned, and hoping to work some partnership there. But in closing, again, I want to thank the opportunity to come talk today. As I put in the chat, you know, if you're interested in getting involved in AquaWatch, we'd love to hear from you. And we're particularly interested in hearing more from the end user community and what types of products would they need, what kind of fit for purpose products that would help them and help the satellite community, you know, build those types of products that are useful, because success breeds success. And we, you know, we can keep building new satellites, but we have to go the last yard to get it into the hands of the people that can utilize this information.
I just want to say briefly, thank you, Frank, for moderating, and thank you, panelists, for sharing all your knowledge and information. Thank you, attendees, for the great questions. If your question was not addressed, or if you have any follow-ups, please don't hesitate to reach out to the panelists themselves. And with that, I'll pass it over to Max.
Thanks, Adam. Just one last note from me, and I'm going to share my screen really quickly. As I mentioned at the beginning, Water Data Forum is a series, and we have a couple of sessions coming up. Next month's session, we have the date locked in for the 22nd, and that's going to be focused on data-driven network optimization, distribution network optimization, so focused on more of the application of sensor data collection and management for drinking water systems in utilities. And then the following month, we'll be looking at realizing the Internet of Water, looking at interoperability between water data sets and across sectors. And we'll have the date for that confirmed shortly. So you can find this and other Water Data Forum editions on the Cleveland Water Alliance website, and you can find the recordings of this session as well as past sessions on our YouTube. With that, I'd like to thank everyone very much for your attendance today. Oops, get out of this screen share. And Adam, unless there's anything else, I think we can call it a day. And thanks everyone again for attending, and have a good rest of your day.
Thank you.
Thank you. Good.